1, 2. Well, thank you very much. It's a pleasure and an honor to be a member of the Academy. I don't think it has sunk in yet. It will take a while. I know when I received notification of being elected, actually it was an email that said congratulations about the Academy, and my reply was, I don't know what you're talking about. I had absolutely no idea. I grew up in central France in a rural landscape that you see here. I have experienced in my youth bitter cold in this part of the world than I ever did in Greenland and Antarctica. I've always been attracted by the polar regions, but I cannot exactly point out to why this is so. A lot of my friends wanted to cruise in the tropics and I wanted to go to the poles. But once I got the chance to visit Greenland and Antarctica, I absolutely fell in love with these regions because the landscapes are so fantastic in this part of the world, and this hasn't changed yet. It's been a winding road to get here from my little suburban area. I have a training as an engineer in France and aerospace engineering. When I moved to the US, as I've started getting interested in research, I didn't think I could do research. I was not smart enough to do that. I discovered the beauty of academic freedom in doing research when I came to the US. I actually got a degree in electrical engineering. I also did some astrophysics. So it was a long winding road before I got to science. When I joined JPL in the late 80s, it was a burgeoning place, and I learned a lot. And in retrospect, I think I was there at the right time, at the right place, sort of doing the right thing, even though it didn't start from day one. And in the early 90s, a technique of satellite observation emerged from JPL people like Dick Goldstein and others, which is called SAR interferometry, where you combine radar images taken from space in a coherent fashion and generate these fringes that you see on the right that express the motion of the ice at millimeter precision. Each full cycle of fringes here is a 28 millimeter variation in speed of the glacier, and you can see in this actually it's not a glacier, it's a floating ice shelf, the rifting of the ice shelf, and this happened at a time where we didn't even know how fast most of the glaciers were flowing. We didn't know how thick they were. We had no idea what the ice sheets were doing, and we had a technique that was just blowing us away by the amount of information and precision that was in there. I got also very interested in that. This is a difference map with interferometry technique where you see the step over between grounded ice, this is Pine Island Glacier, it's 30 kilometers wide, and floating ice. And you can see that little step over due to the flapping of the ice with the tide with very high precision. And you can actually pinpoint exactly where the ice encounters the ocean. Something that field people were dreaming to do, and it's really challenging to do in the field. And in fact, there was areas where people thought this is where the ice meets the ocean, and they were off by 100 kilometers. And with these techniques, we could actually pinpoint it within 100 meters. So I sort of walked through that at JPL with my interferometry goggles around Greenland and Antarctica, and I was a polar explorer. I was looking at things that people had never seen before, and of course this was very exciting. And now we are bringing this level of measurements to mapping Antarctica. These are flow lines of the ice of the Antarctic, where we have precision in the mapping of the deformation of the ice that approaches 15 centimeters per year. Even with GPS on the field, it's difficult to measure with that level of precision. And we can see the dynamics of the ice. And it's very important to study these glaciers because they carry most of the mass from the ice sheets from the continent into the ocean. And at low elevation, that's where they interact the most with climate change. At the same time, as this technique of satellite techniques emerge, NASA launched a bunch of airborne programs with the goal to figure out what the heck is going on in the polar regions? Climate change is happening, and we have no idea what Greenland is doing and Antarctica is doing. So the program started in Greenland, which was a little bit more affordable, and they measured the ice sheet with laser altimetry, with radar sounders, and we learned a lot with this data. And it started in 1993, and it's been carrying on. Actually, this year is going to be the last year that these operations are carried out. And in 2002, we started going to the Antarctic, to West Antarctica, because we knew some important changes were taking place. And the first flight to the Antarctic, I remember one of the most vivid days of my life, apart from the birth of my children. We were 25 people in the cockpit, looking at the glacier we were flying above. I got the chance also in these early years to work with some of the giants in the field, people who worked doing IGY and explored Antarctica for the first time, looking at glaciers. Bob Thomas was one of them. He was the leader of the program at NASA, and he was one of the proponents of this marine ice sheet instability theory. Very early on, with simple models, people understood that an ice sheet grounded on a normal slope, a slope going up as you go in the inland direction, has a lot of stable position for an ice sheet. But if the ice sheet rests on a retrograde slope, go back, please. Okay. I meant to press on the pointer. I apologize for that. Okay. Here we go. Retrograde slope, there's only two stable states. Either the ice goes to the edge of the continental shelf or becomes a floating ice shelf. So when people saw that, they thought, well, we see some parts of Antarctica that have a retrograde slope. How come we have an ice sheet there? So others said, well, probably because your theory is wrong. The theory is not wrong. In fact, the people who studied glaciers in Alaska, tidewater glaciers, knew about this. They saw glaciers retreat into the deeper bed very rapidly in an acclimatic fashion, and then they stop the retreat once they reach a prograde slope where it gets more stable. And the reason for that is that along a retrograde slope, the thickness gets larger inland, and the rate of spreading of the ice increases with the cube of the thickness. So we learned a lot about the way ice sheets melt because we see a system that is changing. In science, it's very exciting to look at the system, what is changing, because you learn about the processes that are driving it. But an idea deeply encroached in our mind is that the way an ice sheet melts is what you see here. It's melting from the surface. And this is perpetrated by the media, and it's still encroaching in the mentality of a lot of scientists. So you replace a highly reflective surface of snow by a less reflective surface of ice, and then you put water on top, which is even more absorptive of radiation, and you have a runaway phenomena. These supraglacial rivers of ice, they run on the ice sheet, and they fall all in a hole at one point or another that communicates with the bed of the ice sheet. That rises the water pressure at the base of the ice sheet that lifts off the ice from the bed, and then the ice can slide faster. Right. Fortunately, we know now that this is not a main process of change of the ice sheet. What happens is that these subglacial channels somehow connect to each other, eventually to the ocean, and then the pressure is released and it stops. Right? And in fact, as you melt the ice sheet more and pour more water in the system, it will happen sooner, but it will also stop sooner. So we know that most of the changes taking place in the ice sheet right now are not in the interior regions. There's not change in snow accumulation, for instance. It's happening at the periphery, right where the glaciers meet the ocean. That's where all the changes are taking place. So this is a glacier in Greenland called Elheim. This is a calving event recorded by Denise Holland from NYU. The iceberg that you see detached here in accelerated motion is 800 meters thick and about 1 kilometer wide. The glacier is 12 kilometers wide. And in that traditional book of glaciology, you learn that when the glaciers meet the ocean, they calve into iceberg. End of the story. What we discovered is that there's a lot of action taking place below the surface that you can't see, which is the interaction of ice with the ocean. Right? And calving is just a participant to that. So let me explain to you how this works. This is the Antarctic, and the water column in the polar ocean is organized very differently from the tropics. You don't have warm water at the top and cold water at the bottom. It's the opposite. You have cold water at the top, and the warm water, saltier, is at the bottom, 400, 700 below the surface, right? If you want to find it, you cannot just peer from the boat side. You have to lower instruments very deep down, close to the glaciers. And that mixture of ice and seawater has a melting point of -2 degrees at the surface, and when the water is at 2 kilometers depth, it becomes -3.5. So there's plenty of heat available to melt the ice from beneath, and especially in the deeper part of the ice, the grounding line, where we have rates in the Antarctic approaching 100 meters per year, whereas at the surface, the rate of turnover is more like 1 meter per year. So it's 2 orders of magnitude difference from the top and bottom. And by melting the ice from below, you remove a lot of basal friction in front of the glacier. You remove a lot of basal resistance to the flow, and the glaciers feel that tremendously, right? Much more than the feeling at the surface. So the heat for the Antarctic comes from the Antarctic circumpolar current, which circulates clockwise and is pushed by the westerly winds. And you might ask, how is this changing with climate warming, and how is this related to climate warming? So what happens in the Antarctic is that we don't have a strong snow albedo feedback. It's too cold to melt the snow. It's not melting very much, in fact. And then we have the depletion of the ozone hole, which cools the stratosphere. So the temperature differential between the Antarctic and the rest of the world is actually getting bigger with time. And that strengthens the winds around the Antarctic. And not only that, they contract towards South Pole. And if you remember Coriolis effect, it pushes the surface waters to the left in the southern hemisphere, and the bottom water, the warm water, to the right towards the Antarctic continent. So that promotes more melting of the ice in the Antarctic. In Greenland, we have something similar. This is an imagery from a multi-beam echo sounding. You see the face of the glacier. This is the submerged face part of the glacier, and then the seafloor underneath. And we can see that in Greenland, the glaciers are undercut by the ocean. A little bit similar to what's happening in the Antarctic. The warm water in the Arctic comes from the Gulf Stream. It's a lot warmer than the Antarctic circumpolar current. You have waters coming off the coast of Iceland at +6 or +6 degrees. So the melt rate experienced by the glaciers in Greenland are the order of 300 to 700 meters per year at the bottom. And that's very difficult to observe in situ, because in front of these glaciers there's usually a lot of debris, and they have this annoying tendency of breaking up into iceberg every once in a while. So it's a little bit dangerous to take measurements right in front of them. What's happening in the Arctic is still a little bit of a topic of debate. It's very different from the Antarctic. So you know that in the Arctic, the climate is warming about 2-3 times faster than the rest of the world. There, the snow albedo feedback plays a huge role. We have a reduced snow cover every year on land in the northern hemisphere. There's also a lot more land in the northern hemisphere than in the southern hemisphere. And the sea ice cover is also reduced. So there, the temperature differential between the Arctic and the rest of the world is getting smaller. So the winds that circulate counterclockwise this time around the Arctic get weaker. And not only that, the jet stream starts to wobble. And these wobbles, as the jet stream starts to wobble, it tends to get locked in some places for long periods of time. And the way they are locked depends on the topography. It's not uncommon to see, this is a computer simulation, cold air masses advected along the eastern coast of the US, and warm air masses moving towards Greenland, and warm ocean masses also going towards Greenland and impacting the glaciers in a very significant way. We measure what's happening in the ice sheets very precisely these days with satellite techniques. So techniques that measure the height of the surface with time with lasers, and we see exactly which one is going up and down. It's especially interesting to see in the areas where we know there's glaciers, to see the ice going down very rapidly. That tells us that the glacier is doing something. We measure the speed of the glacier and see how it evolves with time, with interferometry. And since 2002, people have been using the GRACE gravity mission, which is a direct measurement of the change in mass of the ice sheet as a low resolution. So you see these spatial maps here. You see that in Greenland, everything is colored red at some point because melting is affecting, the mass loss is affecting the entire periphery and interior of Greenland. In the Antarctic, the mass loss is limited to the West Antarctic, the Antarctic Peninsula, and there's some hints of action in East Antarctica. You see the mass loss of about 270 gigatons per year over that time period in Greenland. You can see the up and downs from the seasonal cycle. This is Antarctica with an average of 80 gigatons per year mass loss. A lot more variability due to the interannual variability in snowfall. And GRACE can do also all the hundreds of thousands of glaciers worldwide that are very difficult to measure in situ or with other techniques. You can see the northern hemisphere dominating cycle and mass loss of 200 gigatons per year from the glaciers. And then you don't have to be an Academy member to see the curvature on these plots, which shows that the mass loss is increasing with time. And when you look at the acceleration of the mass loss over that relatively short period, but we've extended the record farther back than the GRACE period, the acceleration is about 430 gigatons per year per decade. So every decade we had another 400 gigatons per year mass loss. That's about more than 1 millimeter of global sea level rise. If you extend that to the end of the century, and this is not a projection or an extrapolation, we are on course for an 80 centimeter sea level rise by the end of the century, today. So this is clearly much faster than IPCC class of models. The models did not see that coming. And there's a variety of reasons for that. One is that they were poor in observations on ice velocity, ice thickness. We still have a very poor description of the bathymetry around the ice sheets. I spent the last 10 years of my life mapping bathymetry around Greenland. And it was a fun job because I was the first one to do it. It's a good thing to do in science, to be the first one mapping something. You don't have to push it too far to do something breakthrough. The models don't capture the change in wind in the Southern Ocean. They don't capture the way that warm water is carried onto the continental shelf and reaches the glaciers. If you want a model to do that, you cannot run it at 100 kilometer resolution. You have to run it at a kilometer resolution. And we cannot do that with global models right now. Am I running out of time? This is a map of the Greenland ice sheet and Antarctica with the ice removed. And some of these floodgates that are very important for the future here that hold a lot of marine ice, about 3 meters in Greenland, have been opened up by climate change. And there's also a lot of floodgates in West Antarctica and some in East Antarctica that I'll talk about. The first glacier that caught our attention was Jakobshavn Isberg, which had the floating ice tongue that collapsed in 2002 because of warm water from the Atlantic coming in here. And the glacier multiplied speed by a factor 2. And in 2012, it was moving 3 times faster. And the ice is retreating down a deep Grand Canyon with retrograde slope. And this is an example of marine ice sheet instability. In the northeast part of Greenland, we had an ice shelf that fell apart, and it took about 8 years to completely fall apart. The speed up is not as spectacular, but we discovered that this glacier for a long time was anchored on a ridge, and once it destabilized from the ridge, it started doing its thing. In Antarctica, all the red spots here are areas of rapid change, we saw ice shelves collapse in the 1990s and 2000 in the peninsula, and witnessed that some of the glaciers not only felt the effect of less flow resistance in front of them, they sped up by a factor 3 to 8 in response to that. Now, if you do a thought experiment and do this all around the Antarctic and collapse all these ice shelves, and say you speed up the glaciers by a factor 6.5, you raise sea level by 4 meters per century. And 4 meters per century was exactly the rate that was observed for several centuries during meltwater pulse 1A 14,000 years ago, when a lot of the ice sheets in the northern hemisphere fell apart, and some parts of Antarctica as well. So it's not completely realistic to see that because it's happening in the Antarctic Peninsula. We paid a lot of attention also in the western Antarctic ice sheet sector. In the Pine Island and Thwaites Glacier, this glacier is 120 kilometers wide. All of these glaciers feel the effect of more warm water. They are speeding up by 75%. They are retreating at 1 to 2 kilometers per year. There's not a single glacier on the face of the earth in Alaska, alpine landscape, or Himalaya that retreats at these rates. These are the fastest retreating glaciers on the face of the earth. But you wouldn't see it with the naked eye because it's happening a kilometer below the surface. You can see it with satellite techniques. Another glacier that caught our attention is Totten Glacier. This is a single glacier in East Antarctica which holds 3.5 meters sea level rise. You don't want to tease that one, but it's already showing signs of mass loss and thinning. And in 2016, an Australian expedition found the presence of warm water in front. That explains what the glacier is doing what it's doing right now. So we are on a trajectory of 1 meter per century, but we know from paleo records that when the climate 125,000 years ago was a little bit warmer than today, or maybe just about the same, sea level was 6 to 9 meters higher. Right? That means a lot of marine part of Greenland was gone, West Antarctica was gone, and some part of East Antarctica to be identified was gone as well. It's likely that if we push the system in the same state, this will repeat itself, except the paleo record does not tell us how long it's going to take. Damage doesn't take place with multi-meter sea level rise. It starts with 1 meter sea level rise. We have a lot of people living within 1 meter of sea level rise, a lot of infrastructures. San Francisco doesn't have an airport with 1 meter sea level rise. So we have to communicate this risk, and one of the difficulty when we talk about polar regions and sea level rise is that the community tends to be conservative. If you're conservative, you look like a better scientist than if you actually tell the facts that are pretty scary sometimes. We will have to move or to protect. Some people will be able to protect. Some people will have to move. And it's coming with all kinds of issues because the poor populations will be affected the most. And you're going to have massive immigration from climate change instead of violence as we're experimenting today. My last slide. So what can we do instead of the Band-Aid solution, which is to adapt, which we will have to do anyway, is to unplug the experiment before the patient dies and avoid a commitment to multi-level sea level rise. And I think that commitment is not way ahead of us. I think we are right here. We already unplugged a lot of the systems in Greenland and West Antarctica, and the turning point would be to do the same thing in East Antarctica. The solution is to transition to a carbon-free energy rapidly and worldwide, which means that we have to share the technologies with countries who don't have it. But that won't be enough. From an ice sheet perspective, I don't think that the current climate system we have is a stable solution for our future. Sea level will keep rising. So stabilizing our CO2 concentration in the atmosphere, that's a very important step if we can achieve that. But we also need to work on techniques to sequester the extra carbon that we unleash in the atmosphere to bring back the climate system to, well, what it was about the 80s. 80s were good years. That's when the climate system started to deviate from the natural variability. And so that means you have to look at the carbon concentration 30 or 40 years prior to that to find something that would be more of a sweet spot. And this is my motherhood statement, but at the end of the day, what we're looking for is a world informed by science instead of Twitter, and that produces clean energy, maintains clean air, clean water, and provides sustainable and equitable development. And who doesn't want that? Thank you.
Okay. I don't think we have time for questions. But thank you. It was wonderful. Our next speaker, representative of Class